In this lesson, we're starting with the graph and drawing some conclusions from it and maybe supporting those conclusions algebraically. So we're starting with what I hope would be an easy example for you, looking at a graph and trying to find particular data about that real-world situation in the graph. So in this graph, they are representing a real-world situation, the value of a stock, with this polynomial function. You see it represented as v of d is 0.002 times d to the fourth power, blah, blah, blah. And d represents the day of the assessment, and v is the value of the stock. So what you're being asked in part A of this problem is to use the graph to estimate the value of the stock on the 10th day. So we look at our graph and we find the 10th day. So the 10th day is about here. And where that x value of 10 is crossing our graph, it looks like it's approximately 32, 33. So we would say approximately maybe $32. So that's our estimate. And then it wants us to confirm our estimate algebraically. Well, if d is 10, then when I plug in 10 for d, I would get something close to $32 if I'm confirming my estimate. If my estimate is completely wrong, then I'm going to be nowhere near $32. So what you're going to do in your calculator now is to find the v of 10, and that means plugging into your calculator all of this loveliness, 0.002 times 10 to the fourth power minus 0.11 times d, times 10 to the third power plus 1.77 times 10 squared minus, whoops, too many passes, 8.6 times 10 plus 31. So all of that is what you're typing into your calculator. And if you have the TI-84 Plus, then you can type that whole thing in and see it as it's typed in to make sure that there's no error in what you typed in. If you're using a scientific calculator, you just kind of have to trust that the calculator is using order of operations properly. Okay, so 0.002 times 10 to the fourth minus 0.11 times 10 to the third. Let's try that again. My calculator misunderstood me. Plus 1.77 times 10 squared minus 8.6 times 10 plus 31, and it's $32, right on the money. Take a moment and work through the your turn below. It's still referring to the same graph as the last problem. We're using the graph of a relation or a function to determine its domain and range. So once again, remember what domain is. Domain is what kind of x's am I allowed to input? What kind of x's exist in my graph? And in these functions, they're not actually giving us the equation, so we can't make any decisions about what x is allowed to be. as far as what I've discussed in a previous lesson, like taking the square root of a negative number, dividing by 0. That's not necessarily what we're thinking in these problems. We're just looking at what kind of x's are in my graph and what kind of y's are in my graph. It doesn't tell us whether to use interval notation or set notation, so you can probably get away with using either one depending on which one expresses your answer more clearly. All right, so let's look at domain for part A. So for part A, what I would like you to notice is that if I go any further left on my graph than -2, there's nothing else happening. So my domain starts at -2. So I'm going to use this in interval notation. And since that is a closed circle at that -2, I'm going to put the bracket there. So bracket -2, and I scan my graph and I go looking to the right, looking to the right, looking to the right, and then I get to 6, and after 6, nothing's happening. So 6 is a boundary of my domain, but again, make sure that you're paying attention to whether it's a bracket or a parentheses. Because at 6 there is an open circle, that means I have a parenthesis there. For my range, if I'm looking at my graph from bottom to top, I see that nothing is happening until I hit 0. And then going up my graph, I see that after 4, I have no more values in my range. And since there doesn't appear to be an open circle at the 4, I'm going to put a bracket there. So my domain is from -2 to 6, with -2 being included and 6 being excluded. And my range is from 0 to 4 inclusive. For part B, let's look at it pretty much the same way. So I look at my graph from left to right, and I see that things start to happen at -4. But at -4, I do not have a value for y. It's an open circle, so that's why I'm putting a parentheses there. And going to the right, I see that there's something happening at 2. It's jumping, my graph is jumping down to something else. And at that 2, there's an open circle in both parts. So I'm going to close that with a parentheses. Union, because at 2, it starts again, and it goes to positive infinity. And again, remember that since infinity isn't an actual value, we use a parentheses for that. My range, looking at my graph from bottom to top, I see that it goes from -infinity to -2. And then once again, I have to take into account that there's this gap here that picks back up at 6. And that's my domain and range for those problems. In this problem, we're being asked to use the graph, again, to analyze it and estimate where the y-intercept will be. And this is one of the things that we'll do very frequently in this class, is to use the graph of a function to kind of give us some expectation of what we will find algebraically. So here's our y-axis. And remember that a y-intercept is just the point on the y-axis where the graph crosses the y-axis. So it looks like it's crossing it right here at 0,4. And then it's asking us to find the y-intercept algebraically. Remember, the y-intercept will always, always, always have an x-coordinate of 0. So in order to find the y-intercept, all you're doing is plugging in 0 for x. In a function like this is a very easy calculation. This becomes 0 when I plug in 0 for x. This becomes 0 when I plug in 0 for x. This becomes 0 when I plug in 0 for x, and all I've got left to do is add 4, which makes sense that y would equal 4 when x equals 0, which is exactly what we found there. Take a moment to work through the your turn below. In your text, before this example shows up, it talks about what a 0 is, what a root is. They're saying the same thing. Zeros and roots of an equation of a graph are the x-intercepts. When we're talking about the root of an equation, what we're talking about is what does x equal in order for the whole equation to equal 0. So you could think of them as the solutions for the equation. So in this problem, we can think of it as trying to find our x-intercepts. And again, notice what they're asking us to do. They're asking us to look at the graph to approximate the zeros, so to get a general idea of where our answers should end up when we do this algebraically. And then we'll do it algebraically. Okay, so in part A, I have 3x to the third minus 10x squared plus 8x. And in my graph, again, I'm looking for where it's crossing the x-axis. It looks like it's heading at 0, maybe 1.75 and 2. Okay, so those are my approximate zeros. And then I'm going to go through the process of actually solving this thing. All right, so if I have that 0 equals 3x to the third minus 10x squared plus 8x, first thing that I would hope that you'd realize is that this polynomial has a greatest common factor of x. So let's factor that x out. That'll leave me with x times 3x squared minus 10x plus 8. Now I have a quadratic. And a couple of lessons ago, we talked about how to factor a quadratic. This quadratic does factor, because I'd be looking at 3 and 8 multiplying together to get 24. And does 24 have factors that have a sum of 10? Yes, they are 6 and 4. So I'd have x. I know there's only one way I'm going to get that 3x squared, and it's with a 3x and an x. I know the 3x has to multiply by something to either get 6 or 4. I know I'm not going to multiply 3x by a nice pretty number and get 4, so it must be 6. 3x times 2 is what's going to give me that 6, which means this must be 4, so that when I multiply it by x, I get the 4x I'm looking for. The signs in my parentheses are the same because of that last sign in the trinomial being positive. And when they're the same, I look at the sign of my middle term, and it's negative. And when I set each of these factors equal to 0, I can figure out my values for x. So x equals 0, or 4/3, or 2. So 4/3 is equivalent to 1.3 repeating. So this one, I was a little bit off, but the 0 and 2 were accurate. But at least the 1.75 approximation is between 1 and 2, and that 4/3 that I found algebraically is also between 1 and 2. So my approximation is somewhat supported by my algebra. In part B, similar idea. We're looking at the graph to identify the zeros. And they don't look like they have any numbers on that. So we're going to assume that each box is 1. And I'm going to say that that 0 looks like it's at approximately negative 0.2, let's say. So that's my approximation. And now I'm going to solve this algebraically. So that means I'm solving for 0 to equal the square root of 4t plus 1. So in order to solve this equation, I need to get rid of that radical. I square both sides and get that 0 is 4t plus 1. I subtract the 1 and divide the 4, and t is, go in the opposite direction. T is negative 1/4. So my approximation was really stinking close. Negative 1/4 is equivalent to negative 0.25. My approximation was negative 0.2. So my algebra supports my estimation. In this component of your book, they're talking about what it means for a graph to be symmetric over the x-axis, what it means for the graph to be symmetric over the y-axis, what it means for it to be symmetric over the origin. And then in example 5, again, we're looking at the graph first to draw any conclusions about symmetry, and then we're supporting that algebraically and numerically. All right, so part A, looking at the graph, I would hope that you'd think, well, it looks like there might be some symmetry over that line, which is my y-axis. So for part A, first thing to address is whether it's symmetrical over the x-axis, y-axis, or origin, and we're going to say it's symmetrical over the y-axis. And then it wants us to support that numerically. And what they mean by that is take an x value, plug it in, and then compare it to the negative of that x value. So here's what I mean. Let's say I plug in x equals 1. If x equals 1, then what does y equal? Y would equal negative 1 plus 6, which is 5. If I plug in negative 1, if this is truly symmetrical over the y-axis, then y will also equal 5. So if I plug in negative 1 squared is positive 1, but I still have a negative sign there, so now it's back to negative 1 plus 6 is 5. So y does equal 5. But you don't just want to do it for one pair of numbers. You want to make sure you try it for at least 2. So let's try x equals 2. If x equals 2, what does y equal? Well, 2 squared is 4, and then I'd have negative 4 plus 6 equals 2. And again, if this is truly symmetrical over the y-axis, then plugging in negative 2 will also yield 2 for y. So let's do that. If I take negative 2 and square it, it's positive 4 again. But I've got that negative sign out front, so it's negative 4. And then plus 6 is 2. So I have supported that answer numerically, and then it wants me to confirm it algebraically. And what that means is my f of x, remember, was negative x squared plus 6. If it's symmetrical over the y-axis, then replacing x with negative x will give me the same exact equation. So let's work that out. Okay, so if I have negative x and I square it, it becomes x squared. I've still got this negative sign in front of it, plus 6. It's an equivalent equation. So I have just confirmed this algebraically. I'm getting ready to erase this screen, so if you don't have it yet, you might want to pause it. Part B. First part of the instructions are to test it for symmetry over the x-axis, y-axis, and the origin. And looks like it's symmetrical over the y-axis. Looks like it's symmetrical over the x-axis as well. And it looks like it is even symmetrical over the origin. So we're going to say it has all symmetry. Right? So that's the first thing that they were asking us, is just to look at the graph for the symmetry. Second thing they're asking us to do is support our answer numerically. So if I replace my y with negative y, and I get the same equation, then that covers it being symmetrical over the x-axis. If I replace a value with its opposite as far as the x is, and I end up with the same value, then it's symmetrical over the y-axis. So let's do one thing at a time, and then we'll look at the symmetry over the origin. All right, so if I plug in x equals 3. So if x equals 3, then what does y equal? Well, 3 squared is 9. I would subtract the 9 from the 25 and get 16. So y would equal positive or negative 4. And at 3, if I plug in negative 3, if this is symmetrical over the y-axis, then I should still end up with y equals positive or negative 4. Okay, so if I plug in negative 3 into my equation, well, negative 3 quantity squared is 9. Again, subtract that from 25, I get 16. Y squared equals 16 means that y equals, again, positive or negative 4. In the interest of time, I'm just going to use 1 point to verify numerically symmetry over the y-axis. I'm going to use another number to show it over the x-axis, and then move on from there. Okay, so this has confirmed y symmetry. If I plug in x equals 4, actually, let me go backwards, because now I'm verifying symmetry over the x-axis. So if I plug in a value for y, let's say 3, what does x equal? If I plug in y equals 3, y squared is 9, subtracted from 25 I get 16, x squared this time equals 16, so x would equal positive or negative 4. And if I plug in negative 3, and this is truly symmetrical over the x-axis, then x will equal positive and negative 4 again. So negative 3 squared is 9, 25 minus 9 is 16. Square root of x squared equals 16 means that x equals, sure enough, positive or negative 4. And we have just shown this x symmetry. And then finally, if I replace both x and negative x and y with negative y, I end up with an equivalent equation. Okay, so if I have that x equals 3 and y equals 4, we already know that that is a point in our graph. And when I do that, it's true. And when I plug in negative 3 and negative 4, it's the exact same graph. It's the exact same validity. And then I could go through and confirm all of this algebraically. If I plug in negative x, I would end up with the same equation. If I plug in negative y, I would end up with the same equation. And if I plug in negative x and a negative y, once again, same exact equation. So it can be confirmed algebraically. Finally, this last bit in your text is taking that symmetry to another level and giving it kind of another way to describe it using vocabulary. If it is symmetric over the y-axis, then we say that it is an even function. If it is an odd function, then we say that it's symmetrical over the origin. All right, so notice in these instructions, they're asking you to start with the graph in order to determine whether it's even, odd, or neither. And then they want you, again, to confirm it algebraically. So if you don't have a graphing calculator, remember that you can use Desmos. So the first graph that they wanted us to look at was 2 over x squared. And looking at this graph, I would hope that you would notice that it looks like it's symmetrical over the y-axis. And if it's symmetrical over the y-axis, remember that means it's even. They want us to confirm that algebraically, of course. Well, remember what that means. If I take y equals 2 over negative x squared, I should end up with the exact same equation. Well, negative x, quantity squared, is just x squared. That 2 I'm not doing anything to, so yes, it is the same equation. And it's asking if it's odd or even to describe the symmetry of the graph of the function. It is symmetrical over the y-axis. when we graph y equals 4 times the square root of x, you would notice that there's no symmetry over the y-axis, and there's nothing at all going on in that third quadrant, which is where something should be happening if this was symmetrical over the origin. This is neither as far as even or odd. Confirming algebraically. If I plug in negative x, this does not equal the same thing as 4 times the square root of x. I could be taking the square root of a negative number now, and you know that's not allowed. Okay, so that's not equivalent. And it also doesn't equal the opposite of 4 times the square root of x. For part C, again, looking at that graph, minus 2x. Okay, so I've got my graph, and it looks like it could be odd. I'd hope that you'd notice it's definitely not even. It's not symmetrical over the y-axis, but it could be symmetrical over the origin. Okay, so let's check that algebraically. So I'm going to write down odd with a question mark because I haven't verified it algebraically yet. So if I plug in negative x for x, in order for it to be odd, I should end up with the exact opposite of my original function. Okay, so let's check that out. So when I take that negative x to the 5th power now, I have negative x to the 5th. When I take this negative x to the 3rd power, I have negative x to the 3rd being multiplied by negative 2, so that's plus 2x to the 3rd. And this is minus x. And since this function is the opposite of the original, then it is odd. It's not F, it's H. Meaning it is symmetrical over the origin.